The unit that we're going to start today is on radicals, and today we're going to specifically talk about simplifying radicals and how we can add and subtract radical expressions. So let's first start off by talking about simplifying radicals. Now when we say that we want to put a radical in simplest form, we are trying to get a radical so that there is no perfect root that's remaining inside the radical. Okay, so in simplest form, the simplest form of a radical is when there is no perfect root remaining inside the radical. So for example, if we had the square root of 24, this is not in simplest form because there is a perfect root that's still inside the radical right now. For example, 4 is a perfect square that's still inside of that radical because 4 is a factor of 24. So what we can do is we can rewrite the square root of 24 as the square root of 4 and the square root of 6. And that way we can simplify the square root of 4 to 2. So this would be equal to 2 root 6. All right, let's take a look at example 1. So we have the square root of 25a to the 6. We want to simplify this as much as possible. So we'll start with the 25. So we know 25 is a perfect square. So by taking the square root of 25, we end up with 5. Now with a to the 6, we want to think about what can I multiply by itself in order to get a to the 6. So in this case, a to the third times a to the third is going to give us a to the 6. So we would say a to the 6 is a perfect square. Now another way to come up with a to the third is to say, well, as long as the exponent, now make sure it's the exponent and not any other number under the radical. But if the exponent is an even exponent, we know it's a perfect square. So what you can do as a shortcut is you can take the exponent and divide that exponent by 2 if it's under the square root. So in this case, 6 divided by 2 gives you 3. So when you take the square root of a to the 6th, that's equal to a to the third. But again, I'm going to emphasize that that only works if you're working with the exponent. It does not work with the 25. You cannot divide the 25 by 2 to get its square root. All right, let's look at the second one. We have the square root of p to the 12th and q to the 4th. And we'll take each part separately. So p to the 12th, what times itself will give us p to the 12th? Well, if we do p to the 6th times p to the 6th, that's going to give us p to the 12th. With q to the 4th, again, think about what times itself will give us q to the 4th. That would be q squared times q squared. So by taking the square root here, we'd end up with p to the 6th and q squared. Again, because both the 12 and the 4 are exponents under the square root, you could do 12 divided by 2 to get the 6 and 4 divided by 2 to get the 2. Let's take a look at example 2. We have the square root of 54x to the 5th. Now for these ones, because 54 is not a perfect square, we're going to want to see if there are any factors of 54 that are perfect squares. Same with x to the 5th. X to the 5th, you can see here is an odd exponent, will not itself be a perfect square. However, there may be factors of x to the 5th that is a perfect square that we can take out. So what I'm going to do is I'm going to rewrite this expression with two radicals, one that has perfect squares under it and one that has everything remaining in it. So starting with the 54, I want to think of perfect squares that could be factors of 54. So in this case, 9 is a perfect square that's a factor of 54. So I'm going to put 9 under the first square root. Then for x to the fifth, I want to think about if x to the fifth has any factors that are perfect squares. Again, remember that when it comes to exponents, anytime you have an even exponent, that's going to be a perfect square. So in this case, x to the fourth is a perfect square. So now I can write square root of 9x to the fourth all under that first square root. Now if I take that out, what do I have left? Well, 54 divided by 9 is 6. And then if I take out x to the fourth, I'm left with just an x. Now I'm going to simplify that first radical, which now only has perfect squares in it. So the square root of 9 is 3, and the square root of x to the fourth is x squared. So this is going to be 3x squared times the square root of 6x. And that's as simplified as I can write this expression. All right, let's look at the second one here. The square root of 162, x cubed, y to the fifth. All right, so the same process here. We want to take each part and see if we can find any perfect squares that are factors. So look at the 162 and see if we can find any factors of 162 that are perfect squares. In this case, 81 is a factor of 162. That's a perfect square. And then we have x cubed. Again, this is odd, so let's try to find an even exponent, which would make that a perfect square. So x squared would be a perfect square. And for y to the fifth, we can take out a y to the fourth, and that would be a perfect square. So in my first radical, I have 81 x squared y to the fourth. And what I have left, so after I take out the 81 from the 162, I'm left with 2. When I take out the x squared from x cubed, I'm left with x. And when I take out the y to the fourth from the y to the fifth, I'm left with y. All right, so now we can go ahead and simplify that first radical, now that everything inside that radical is a perfect square. So the square root of 81 is 9. Square root of x squared is x. Square root of y to the fourth is y squared. And then we can write the square root of 2xy after that. All right, now that we've taken a look at how to simplify radicals, the next thing we're going to talk about is how you add and subtract radical expressions. Now, the one key thing to note here when you're adding and subtracting radical expressions is that you can only combine radical expressions by adding and subtracting if what's under the radical is the same. So here, if we have a times the square root of x plus b times the square root of x, because what's under the radical in both cases is the square root of x, we can combine a and b together and write that in front of x. All right, so taking a look at our first example here under example 3, we have 3 times the square root of 5x minus 2 times the square root of 5x. Now, because what's under the square root in both of those terms is 5x, we can combine these. So we combine the 3 and the minus 2. So 3 minus 2 is equal to 1. And then what's under the square root is going to stay. So this is going to be equal to 1 times the square root of 5x, or just the square root of 5x. All right, in the second one here, we have 6x squared times the square root of 7 plus 4x times the square root of 5. In this case, because the first term has a 7 under the square root, and in the second term, we have a 5 under the square root, we won't be able to combine these terms. Now, one good thing to check is you want to see, well, can I simplify those radicals and then combine them? Well, for 7, there are no perfect squares that are factors of 7. And for 5, there are no factors of 5 that are perfect squares. So that means there's no way for us to simplify this and then combine. So we can just say we can't combine these. You can add them, but you won't be able to combine them into one term. All right, and then the last example, square root of 12 plus the square root of 75 minus the square root of 3. So again, looking at this problem, you can see, well, it doesn't look like we can combine these because we have different numbers under the square root. But before you say that you can't combine them, double check and see, well, are these radicals all simplified? So for the square root of 12, are there any factors of 12 that are perfect squares? In this case, yes. 4 is a factor of 12, that's a perfect square. What about for 75? Yes, 25 is a perfect square, that's a factor of 75. So we can go ahead and take those out and simplify both the square root of 12 and the square root of 75 and see if we're able to do anything after simplifying. So the square root of 12, I'm going to make that square root of 4 times the square root of 3. For the square root of 75, we have the square root of 25 and the square root of 3. So that becomes 2 root 3 and 5 root 3. And now you see that under the square root, we have the same thing. 2 root 3 plus 5 root 3 minus, and you can think of this as minus 1 root 3 if you'd like. So 2 plus 5 minus 1, that's equal to 6, and we leave the square root of 3 as is. So our answer here is 6 root 3. So anytime you're adding and subtracting these radicals, you always want to double check, can I simplify the radical first, and then after simplifying the radical, then see if you can add or subtract those radical expressions.